we can see that this variable star is in this spiral nebula, we can figure out how far away this spiral nebula is. And so we had a way to calculate the distance to these spiral nebula that we were trying to figure out if they were inside the Milky Way or outside the Milky Way. And so this is what he did. He noticed that relation, and he started to plot that. So he plotted distance, how far away they were, with the velocity, so the redshift, how red they were, from the galaxies or spiral nebula that Slipher listed in his early observations. And so I'm going to point out that 500 number up there, the slope of the line. We're going to come back to that later, but just remember that number for now. And he calculated, using this method, the universe is 2 billion years old. So as we'll see, if the universe is expanding, as you can imagine, all you have to do is run it back in time like a movie to figure out when it formed. You're just reversing everything. And so, using that method, very linear sort of method, he calculated the age of the universe to be about 2 billion. So we're moving in the right direction still, a bigger number, still not at that 13.8 billion year number, but we're getting much closer than where we started. And so what he found was that the universe is expanding. The universe is expanding. So when the animation comes back up, you'll see a galaxy, and you'll see Earth, and you'll see a wavelength of light between it. And what will happen is, as the galaxy is moving away, not this, though, as the galaxy is moving away from Earth, the light is getting redder. And that's exactly what Slipher saw in his work, that the galaxies that are farther away are redder and are much further away from us. Pause. Okay, we'll let this run for 10 seconds so we can look at it. It's a pretty animation. As the galaxy gets further away, you'll see that this grid is actually the thing that's expanding. That's the physical universe. It's not the things that are necessarily moving away from each other. It's the universe itself that's expanding. And that's the groundbreaking result that Hubble figured out by making that plot that we saw in the previous slide. So, if the universe was expanding, as we said, at a very constant rate, all we would have to do is reverse that expansion into a single point to figure out how old the universe is. The issue is the universe is not expanding at a constant rate. It is changing, or it's not a very uniform sort of expansion. And so, if we reliably want to calculate how old the universe is, what we have to do is try and map out that full expansion history using physics and astronomy observations. So there's two here, decelerating universes. So you might have heard about at least one of them. The one on the left is the Big Crunch. So the universe, both of these are universes where the expansion is slowing down. Now, the Big Crunch is slowing down so much to the point that it collapses back into a single point after a certain amount of time. Coasting universe is expanding kind of at a constant rate. And the one that, at least right now, most closely matches our observations is this accelerating universe, where the universe is expanding and accelerating. The expansion rate is accelerating. So this slide, it's a slight detour, but this is how we map that expansion rate and how it evolves. So the very, very early universe, before we were able to see light, was a hot, dense gas cloud, basically, plasma. Now, that plasma, it was too hot for light to travel through. And in that early sort of nebulous sort of gas cloud, what happened was there were these small quantum fluctuations, and you don't need to know like what that means or anything, just that there's kind of like these waves and ripples that existed in the early universe. And as time went on, and as we saw as the universe expanded, what happened was those quantum ripples expanded along with the expanding universe, and so they grew. And those ripples that we see are called baryon acoustic oscillations, or BAO. Now, as the universe expanded and cooled, those oscillations, those wiggles in the universe, they froze in place because it got too cold, and so those ripples froze. And because they froze, it was, as you can imagine, like if you have like you drop a stone in a pond, there's going to be kind of like a uptick where that wave is. And so what we see is once it froze at a certain point, there was slightly more mass, slightly more gas at the size of that ripple. And so what happened is more galaxies formed at the size of that ripple. And so when we observe the universe and we try and map out where all those galaxies are, what we see is that at the size of this sort of ripple, we see more galaxies. And we use that to go back to understand how that plasma looked, and we use that to understand the evolution of the universe through that. So we're in an age of modern astronomy is precision astronomy. Now, the one on the left is kind of the result that we saw from the baryon acoustic oscillations on the previous slide. And what you'll notice is that the orange curve here, that's our theory. Whereas the blue points in this left plot, those are our observations. And you'll notice that past a certain point, our observations match the theory so well that the uncertainties, so those like up and down yellow bars, they're smaller than the data points themselves. And so our observations match the theory incredibly well for this baryon acoustic oscillation sort of measure. Whereas on the right, each one of these points is its own galaxy. So we live in the Milky Way galaxy with all these stars and planets and things. And this survey, DESI, maps where those galaxies are in the universe, and we have an unbelievable amount of galaxies mapped in the universe. The issue is that when you estimate the expansion rate of the universe using these two methods, they don't agree. So this bottom one with the 73.2, you see there's a number minus 2.5 there, and then at the top one, you see a 67.8. And you'll see that those numbers don't intersect. And so while we've spent all this time mapping the universe so well, these two theories still pose the idea that our model of the universe might not be entirely complete. And how do we work through that to try and figure out the expansion rate of the universe when our two best theories that, as we saw, are very robust and very completely mapped and match our theory very well, are not entirely in agreement. And I will also say longer. That 500 number that we saw in that earlier plot, that's the same number as the 73.2 and 67.8. So Hubble's estimate from that plot at the beginning, that slope of that line, was off by a significant amount. So we've constrained it using these two methods very, very well, at least compared to the earlier estimates. Okay, so still 13.8 billion years. We're still trying to figure out exactly why these are not in agreement, and that's work for, I guess, people in my generation and college generations to figure out in astronomy. Well, we can add these to the plot and complete this full line of this 5,000 years up to the 13.8 billion approximately that we have. And I will leave it with this quote from Hubble that I'll read out. With increasing distance, our knowledge fades and fades rapidly. Eventually we reach the dim boundary, the utmost limits of our telescopes. There we measure shadows and we search among ghostly errors of measurement for landmarks that are scarcely more substantial. The search will continue. Thank you.
mentioned that the universe is not on a steady acceleration, but it's, you know, whatever word you use. Did the universe have like a puberty the way that animals do, where it just like kind of sudden burst of like hormonal growth?
Yeah, so we actually, yes. So the universe did not expand at the constant rate, and a few of the models have a very sharp peak. So you'll notice that these first two, it curves out much quicker. And so what happened is when you do that sort of thing, we reach our present day much faster than these sorts of models, where it takes a much longer time to reach our present day. And you can kind of tell by how far down the star point is. So we think there is a rapid expansion of the universe earlier on, but this is still something that is needed to constrain better.
I just have a bit of a naive question. I was curious about what makes a non-variable star what not to be. So does that mean that the star is like so close that the period is small, and like with our naked eye we can't distinguish like the frequency of what that difference is?
Yeah, so there's a lot of different types of stars. I don't work on stars, I will say, but variable stars have a change in brightness that's much, much greater than more standard stars. So our sun, for instance, it has like ups and downs in its brightness, but the amount, like a variable star has a much, much greater up and down in the difference between the brightest and the dimmest. But it depends on the type of star. There's a bunch of different types of stars and subtypes of stars.
Yeah, thank you. Ending your presentation by putting yourself, probably back in the timeline there, how confident do you feel about our current estimate of the age of the universe?
I would say pretty confident within the uncertainties. There is still, one of the big issues is a lot of the baryonic acoustic oscillation calculations are based on fundamental physics, and we think we understand the fundamental physics very well, but this is before light, and after a certain point, even our best theories, general relativity, breaks down. And so our theory helps us up to a certain point, but there's a limit. And I think these observations give a very, agree enough to a point that I think that 13.8 billion year number is reasonable, plus or minus maybe a billion years.
You mentioned it was a PEAO and decimal model that was accurate, and there's a missing part. But the new line of telescopes, like the Nancy Grace moment, that helps design and kind of close that gap.
I think so. I actually was talking to somebody about this. Well, trying to talk to somebody about this earlier today. There's many modern astronomical telescopes. LSST, which we'll hear about next, is also going to be helpful for this. Rubin, I'm sure, will be helpful for this. I don't know if it actually works on PAO stuff. Does any of these people? Yes, it does, apparently. So great, it'll help, I suppose.
Thanks for your time. How far away does the star need to be for us not to be able to, for the light to reach us, for us to be able to see it? So where does it become dark and we can't see it?
Yeah, so we can, the issue is not necessarily that we can't see the light, It's that our telescopes are not able to resolve the brightness from the star well. And so using Gaia, as we saw in that one animation somewhere. As we saw in Gaia in that one animation, we can resolve those stars very well for the Milky Way. But the next galaxy, so the stars within the Milky Way are fairly close to us with respect to the closest galaxy. And we can't really reliably map an individual star in another galaxy. I mean, I think there are places where we have at least a few. But resolving individual stars is very difficult. And so once you get to a certain point, rather than individual objects, we combine the light from galaxies, and we get the light from all the stars within that galaxy. That's actually kind of what I work on. The light from a bunch of things we can't see stacked together.
So for the two estimates that we have for H0, the slide appears that for the lower value, we are probably running on data from the early ages of the universe, like the prior acoustic oscillations and frequency minor field oscillations. Right? So is it possible that there's perhaps different rates of expansion over the history of the universe?
Yeah, so in the early universe, a lot of this was, I was talking about baryon acoustic oscillations and using the baryon acoustic oscillations to estimate the expansion rate of the universe. And the question was, using these other sorts of models, since a lot of these are based on this early universe model, can we does the expansion rate of the universe change using other sorts of models? So the early root is that top part, and so a few of them, I guess the C, D, and E, use baryon acoustic oscillations. But A and B, so A is just the cosmic microwave background. So that's the first light that is produced in the universe, is from the cosmic microwave background. And you'll see that that one also actually is pretty consistent with like the average value of these observations. So the expansion rate of the universe, like as we have seen, does change over the entire lifetime of the universe. But even without the baryon acoustic oscillations, just the result we see after light starts to pass through the universe in A, that also agrees pretty well with the this 67.8 number. One more question. If there's another question, yes.
So since this is your life and you study this, is there any leading theories or that are your favorite, like a hot take on the discrepancy between these? Or is that something you're actively exploring right now? Because there's probably a lot of people exploring it.
I try and stay out of these arguments, personally. I mean, I'm an early universe cosmologist. I don't necessarily work very closely with the individual galaxies, especially at the the root, as in like local universe kind of things. So I'm personally probably leaning towards the early root because I like the cosmic microwave background and I like baryon acoustic oscillations. But I will avoid saying anything negative about the late model. I will just say, personally, I work on the early root. Thank you very much for coming.
Give me 1 second. I'm going to go into the trivia answers and announce the winners. All right. So, the answers for the trivia answers. Hold on, sorry, I have to move my cursor. It's gonna bug me if I don't move it. Question 1. What is the approximate age of the universe? As we found out from Pip's talk, it is 13.8 billion years. Question 2. Which method is not part of the cosmic distance ladder? It is rotation curves of galaxies, believe it or not. Question 3. How did Lord Kelvin derive his famous estimate for the Earth's age? This was by measuring the temperature gradient at Earth's surface. Question 4. The measurements by the WMAP telescope, pictured here, were one of the first ones to precisely determine the universe's age. Question 5. What is the redshift of the oldest known object in the universe? It is 14.44. This is the farthest thing away that we know of and have observed. And these next questions might be some small spoilers for the next talk, but we'll get there. Approximately how much data will the Rubin Observatory produce? This is about 500 petabytes. This is an enormous amount of data, and it's really hard to process it all. We're going to hear about how we do that in the next talk. What is the most commonly used file format for astronomical images? This is the FITS format, which I should know what it stands for, but I don't. Flexible Image Transport System. Thank you, says the astronomer software engineer. Which object would not trigger an alert from the Rubin Observatory? That is a merging galaxy. They just happen so slowly that it wouldn't trigger an alert. Everything else is on a much shorter timescale. Question 9. The Link Frameworks project is a collaboration between UW and Carnegie Mellon. Believe it or not. And finally, another name for the shift and stack method is the synthetic tracking method. So, there were actually 5 teams tied for first. 5 teams got 6 of the questions correct. These questions were kind of hard. So good work to those teams. The first team to get 6 correctly, which may be a team of astronomers, maybe not, we'll see. And also, if you are one of the winners, please come up and talk to us after the show and we'll get you a prize. The first winning team is, most of us haven't gone to AOT, but that's fine. Nice. Good work. The second team is Team Tojo. Nice. Next up is Team Voyager. I barely know her. The next team that got 6 points is, where's George? And finally, Team Space Ghost Coast to Coast. Good work. If you are one of the winning teams, please come see us afterwards. Good work. We'll take a very short intermission to set up the next speaker, but we want to make sure we give them enough time. We'll see you in like a few minutes.
That's what I.
part 2 of our Astronomy on Tap number 107. We are now going to hear from Maxine West, who is a link framework software engineer with the Astronomy department. And she's going to tell you more about what that means. Take it away.
Hi everyone, yeah, I'm Maxine West, and I'm a software engineer with the Link Frameworks project at the University of Washington. I did have a bachelor's degree, so it's not that impressive to say my academic pedigree, but I went to the University of Texas at Austin. So if you hook up horns, yeah, one person, yeah. Oh no, sorry. Okay, so there's actually more Aggies than Longhorns, so that's kind of sense. Whatever, I'll give free information. Okay, so I work with the Vera C Rubin Observatory and the Legacy Survey of Space and Time. So we're going to give kind of an introduction part. Sorry, thank you. I will try to talk as loud as I can. But so just as like a raise of hands, who here has heard of the Vera C Rubin Observatory before? Okay, so like approximately 75%. So if you've already gotten all like the pro-Rubin propaganda from like previous Tap talks, you can go like pee or get a beer. Because I feel like since so many people work with Rubin at UW, it's probably repeated a million times. But I will give a brief, approximately 10-minute introduction into the Rubin Observatory. And then I'll talk a little bit about, computer science problems and how we as software engineers work through and help astronomers solve those problems using computers. So, just as a little intro, Vera C. Rubin was an astronomer. She discovered the galaxy co-rotation problem, which is basically she discovered the rotation of galaxies and determined that the outer edges of those galaxies were rotating at approximately the same speed as the inner sections of those galaxies, which is not what you would expect with normal relativity and gravity, and which pointed to the fact that there was maybe some other mass in the universe that would indicate this rotation. So she's kind of the not the discoverer of dark matter, but the discoverer of the thing that dark matter explains. And she was also an advocate for women in astronomy. So she was a real girl's girl, and we support her for that. And she got a very big fancy telescope that I'm going to talk about named after her. So yeah, so shout out to her. I have never been able to figure out why you're supposed to call it Vera C. Rubin Observatory, never supposed to call it VRO. I have never been able to figure out why they're so insistent that you don't call it VRO, but don't call it VRO if you want to abbreviate it. So just keep that in mind. Okay, so what is the Vera C. Rubin Observatory? It's a brand new construction finished last year, and the first images, which we'll show a little bit of later in the talk, were released last year. It's located in Chile in the Atacama Desert, which is in sort of like north central part of Chile, and it's this location that is this high desert between two mountain ranges that is very good for astronomical observations because it's very high and dry. It's actually like a place that NASA and other space organizations go to test conditions on extraterrestrial planets for like rovers and stuff. But you can also look up in the sky, and because there's less atmosphere and there's almost no weather, it's a great place to also look both up and down and study space. So there are also a lot of other not as important but also kind of cool observatories that are right next to Rubin. But this is the one that's the important one. This is Rubin Observatory, and it's the project that I work on and a lot of people at UW work on. And the basic concept of Rubin is that it's a survey telescope. So it is a massive camera, the largest digital camera ever created, 3.2 gigapixels, which is a unit you probably never heard of in terms of cameras, but it is just an absolutely massive camera that it takes pictures of the sky sequentially, and the goal is to create the deepest possible image of the sky every 3 nights using this massive camera over the course of 10 years, building up the largest time lapse of the universe ever made. So this is just kind of an explanation of the actual telescope. So you can see this is the very big camera. The camera itself is like the size of a small car. These very tiny people around it. the actual telescope assembly, which is an 8-meter telescope, is about the size of like a house, and it can move very rapidly and point at new targets in the sky. And so the basic idea is that we will just point it, and as you can see with this demonstration, it's sort of just, it actually doesn't look as neat as this. It like takes random points in the sky, and they also rotate, which is really annoying if you do data analysis on them, because you expect telescopes to sort of like point in a singular direction. But you know, that's part of my problem, so that's all. But the general idea is that we will be able to get the widest breadth of knowledge with the widest depth of knowledge possible of a massive portion of the sky, the entire southern sky, captured every 3 to 4 days, to build this massive treasure trove of astronomical data. Yeah, the greatest astronomical movie ever. As I said, it can do all of this in multiple filters as well, so it's getting a range of wavelengths using the filters, and it will just build this amazing time lapse of the sky and create a massive catalog of astronomical data for people to sift through. Those people, I'll get into it, but basically, as a software engineer and computer scientist, it's my job is to help to figure out how people are actually going to sift through all this data, because that's kind of the biggest problem when you have a lot of data, is figuring out how to look at it and figure out what new stuff that you discovered. So this is the Rubin first look image. It's like the big like promotional image that was posted. Just a massive field of view of the sky, and you can kind of zoom in here and you can see just like the amount of detail that Rubin is getting in that little tiny corner of this image, and it just resolves to this like amazingly high depth image of the sky, and it is doing this over the course of many nights. This is another great image, and you can see these like little like rainbow streaks. These are asteroids moving across the sky, because another major component of Rubin is asteroid and moving object discovery. So that's kind of what I'm interested in and have been working on. So I don't really care about these like really nice pretty galaxies. I like the little rocks in space. You might ask, like, what is like a science use case that Rubin is trying to solve? And the answer is kind of like all of them. They're kind of like, isn't an astronomical science that isn't going to be touching Rubin just because it's collecting so much data. But it's going to be covering everything from like the solar system and solar system objects all the way out to like these like major questions about dark energy and dark matter that, like as Pip talked about, would sort of like help us figure out how the universe formed and how like these very fundamental questions about the universe. Another big component of Rubin is being able to track as we go throughout and collect as much data as possible, check what stuff changes. So we take a bunch of images, and then every time we take a new image, we check against the already existing data that we have and see stuff that's changed. So we're going to discover a lot of stuff that we don't already know about, we don't know to look for, because it hasn't, you know, you can't really look for stuff that you don't know has changed already. So that's also like a huge component of Rubin. And this is just sort of like a basic thing of like how much stuff in a single image, which takes it's like a 30-second exposure, how much data we're collecting and how much new stuff we're actually getting from each exposure. As you can see, it's a lot of stuff, so that's why they spent $700 million or thereabouts. This whole project required a ton of like new engineering and new technology to be developed. Like I said previously, the development of the largest digital camera ever created, and my favorite part is that they built this like comically large like lens cap for the camera. So when they transported it, they actually put this like lens cap on it, and I just think that's like so funny. Like they didn't like have like some special thing for it. They just built like, yeah, let's put a lens cap. From the camera to the actual telescope itself, which is this amazing feat of engineering, to the actual like data processing and being able to send the approximately 15 to 20 terabytes of data that it's going to collect of raw image data every night from Chile all the way to the various data processing sensors in Stanford or and eventually around the globe. So it's a really incredible feat of engineering. And as an engineer, I can be impressed by it, but I also can't take credit for the project in 2022. So we're generating massive amounts of data, and this is kind of starting to get into where I come in, because when they started developing the LSST project, they basically the project was first funded and sort of developed as an idea in the early aughts, and they basically sort of punted the whole problem of like what the hell are we going to do with the data to 20 years in the future, 10 years in the future, when they thought it was going to start, to figure out, like, because they assumed that the sort of like computer engineering and computer science problems were going to be very different in 10 years when the camera officially came online. Well, the camera actually came online like 20 years after they originally started. And so I was hired on as part of a team of software engineers through Link Frameworks to sort of take a look at these problems and help develop tools and analysis techniques to work with the data in ways that astronomers traditionally hadn't really looked at it. So we're a mixed team of astronomers and research engineers who help develop tools and analysis techniques to help people actually work with Rubin data. And we're based both in the University of Washington here and our sister team at the Carnegie Mellon University. So if you got that question right, that's yeah, the other half of our team is there. So yeah, we work predominantly on Rubin, and we develop tools to help Rubin analysis, but we do have a general goal of helping all survey telescopes, which are becoming increasingly popular in astronomy. A survey telescope is, like Rubin, a thing that doesn't necessarily just look at one single target. If you think about it, it's sort of like the normal paradigm of astronomical research. An astronomer goes to a telescope and says, I want to look at this object for this amount of time, and then the telescope says, okay, you can do that in like 3 months when we have extra time. You get the observations, you look at it, you write a paper on it. Survey telescopes are very different in that they don't have like specific targets. They just look at a wide swath of area, collect as much data as possible, and provide that data to the public or to a select group of researchers. This has a lot of benefits for science in general. Number one is the sort of like time domain aspect. You can collect large periods of time that you couldn't necessarily collect with a normal telescope, because you have to like buy the whole time. Like if you wanted to look at a specific star and see how it changes over 10 years, you'd have to like rent out all the time or a significant portion of the time on that telescope for over 10 years to actually get that time series. But with a survey telescope like Rubin, you can just go to the catalog and collect all of the data points and look at it. It also it also just allows us to check what stuff changes. So stuff that we don't know that we're looking for, when it changes and when it's picked up by the Rubin detection pipeline, you can know about it right when it happens and not have it be just as part of a side project or completely missed entirely. And it also allows for a further democratization of science, because as you can imagine, if you are with a major research institution, it's easier to get access to a major telescope than if you don't have access to your less well-funded university or the less well-funded research program. So by having these large treasure troves of information available, you can more easily provide to a wider swath of astronomers and allow more people to do research, which is just overall better for science. So you might be asking, I should also mention that Rubin is not the only survey telescope in operation or being built. The other major upcoming projects include the Roman telescope, which is an actually space-based survey telescope being built by NASA, the Square Kilometer Array, which is a radio telescope, which is built across a square kilometer, as you can guess by the name, in South Africa, and it's for the purpose of radio astronomy, as well as other projects like the Argus Array, which is this cool project where they're taking off-the-shelf telescope equipment and shoving it into a dome in North Carolina and collecting as wide of a swath of information as possible. So you might be asking, why doesn't everybody just do circuit telescopes? Why hadn't anyone thought of this before? And the big issue is that there's like too much data. It's really hard to work with a massive amount of data. If I ask a telescope to take observations of a specific object, I can download that on my laptop and do the processing by myself. If we're getting 15 terabytes of information per night, you can't necessarily just pull that in and do the analysis yourself on your own laptop or even your own supercomputing cluster at your university. You're going to crash everything and make everyone mad because you're using too much disk space. So that's kind of like where the LINCC frameworks team comes in. A LINCC is a combined team of engineers and astronomers, and our goal is to help develop tools and new techniques that will allow people to actually work with this massive amount of data. So yeah, I think I'll give a kind of like brief overview of like what technologies we've developed and what we're working on, and then I will dive into like an actual like interesting astronomy and computer science problem and kind of talk it through as kind of an example of just like one sliver of the work that we do. So we work with like a lot of our probably most famous or infamous, depending on how you think about it, software is LSTB and HASS, which allows a user to take a catalog and divide spatially on the sky a data set that is partitioned with equal amounts of data points depending on the actual spatial location of the observation, which allows for easier multiprocessing. We also have recently developed HIRAX, which is a low-code framework for machine learning in astronomy. It's geared specifically towards astronomers and allows astronomers to be able to pull in their data sets and run machine learning through that without having to do all of the stuff that you don't want to do when you start a machine learning framework, which is the boring part. We've also developed a solar system simulator, which can simulate observations of solar system objects, and that was through our incubator program. We as part of our mandate, we like bring in external research teams and help them with their research problems, provide computer science expertise and software engineering expertise, and SourceShow was one of the things that came out of that. And the thing that I'm going to talk about a little bit more in the next couple of slides is KBMod, which is a tool for GPU-accelerated motion object detection, which is basically finding very dim objects that don't necessarily appear in a single image, but you can sort of like pull out the observations by stacking up multiple images. So basically, the LINCC frameworks team, as a group of software engineers, is solving a lot of like really important, help enabling science in a lot of like really important fields, from the solar system to extragalactic stuff. And our sort of like end goal is that we will help solve a bunch of problems and really figure out like these like very deep questions like what Pip talked about, like figuring out the age of the universe, figuring out sort of like new frontier physics as we study dark energy and dark matter, and all these like really important like fundamental questions to our universe that help us understand like who we are and where we came from. But I don't really care about any of that stuff, so I'd like to talk about asteroids instead. Because asteroids, they move around a lot, and I'm a masochist at like finding stuff that is hard to find, and so that is a fun computer science problem to me. They also hit us sometimes, and that kind of sucks. But we did hit them once. This image is of the Dart impactor, and I just wanted to put it up there as my demonstration of an asteroid as a little bit of like Earth pride. Because after getting hit for millions of years, we finally got one of those assholes. And a very nice cloud of activity that we slapped it within a satellite. So I'd like to talk a little bit about the KBMod project and finding very dim objects, but first I'd like to play a little game, which is find the asteroid. If you can find it, somewhere in this image is the asteroid 2013 2A228, which I think is a beautiful name for a girl. It's in the center. The image is centered on the asteroid. It's extremely small and hard to see. So 2013 TA-228 is a trans-Neptunian object, which is an object that has an orbit sort of beyond Neptune, as the name implies. And so it's basically out in the Kuiper Belt. This is actually, I think, one of the more like easier to find trans-Neptunian objects, because if you squint closely enough, you can actually see the object in the image, which is not the case for most trans-Neptunian objects. So the big problem with finding trans-Neptunian objects is that they're very dim, they're very slow moving, and they're very far away. I have this like little image that kind of shows the problem. In observations 1, 2, and 3, which are the sort of single frame observations, you cannot really actually see the object. So that kind of sucks. How do we find objects where you can't see it in a single frame? Well, if we know the object's velocity through the image, we can stack up those images and get this very nice little like peak. You can see this like little like PSF or like you can see it in the middle of the frame. So that's really exciting, but the major problem is how do you actually figure out what the orbit of this object is and stack up the images so you can actually find the object and recover from the image if you stack up and add all these values together to find this. And right now our current solution is basically just guess all of the possible trajectories. So that's what KP-mod does. We take an image, and as you can see, this is kind of a demonstration of the actual shift and stack algorithm, but the object moves across the image this way. If you just move the images over and stack them, it looks nice. So our solution is, let's just guess let's assume a bunch of, let's say, thousands to millions to billions of trajectories and guess all of them and see what comes out, which sounds like a great idea. Until you actually consider, wait a minute. So objects don't actually move in linear trajectories across the sky. So that kind of sucks. And it's not like a them problem, it's an us problem. I'd like to thank Pip for the demonstration of parallax, because I realized I just put this graph and was going to explain parallax, but that was a great sort of like introduction to it. But as the Earth rotates around the sun, as you can see, this object is trying to move its best in a straight line or an elliptical orbit, but we're doing loop-de-loops around the sun, and therefore it looks like as the asteroid is just sitting out there in the Kuiper Belt, it's doing a bunch of loop-de-loops. So that's kind of sucks. So how do we fix that problem? We just kind of use like the power of imagination and coordinate transforms, and we are just going to, because if you think about it, if we just like pretended that our observatory was on the surface or at the center of the sun and was looking at the object, it would have a much more linear path, allowing us a much easier time finding new objects. So why don't we just pretend that we do that? Well, let's just assume a distance between the barycenter or the heliocenter, the center of the solar system or the center of the sun, and then let's shuffle all of our image data around so that it looks like we are looking at this image from the center of the sun. So that's actually one of the problems that I helped figure out, was how to actually do that in an efficient way. This is my favorite diagram I've ever made. It's kind of boring, but I just like it. It looks very nice. Basically, you just assume a bunch of different virtual points across the image and fit a new coordinate system over that image, and then resample the image. And it actually turns out that this works very well, and it really does look like you can sort of like much more simulate that the image was taken from the center of the sun instead of the Earth. So that's great. There's still problems, and these are. I wish I could keep going until we had like a completely solved slide, but there's still lots of unsolved problems to actually finding trans-Neptunian objects. Number one, we have a very high false positive rate. So if you can imagine, just taking a bunch of images and stacking them together is going to cause lots of weird imaging artifacts. So we're trying to use machine learning to actually filter out the false positives and find the actual objects that we're looking for. it's hard to tune all of our parameters at the initial phases of searches because it's the known population of trans-Neptunian objects is in the thousands, but the actual assumed from the models of the solar system being created is that there are probably millions of these objects out there. We want to find more of these objects, but we can't know how to find them until we find them, so it's kind of a catch-22 problem. And also, because this is all GPU accelerated code, GPU, I don't know if you've checked GPU prices recently, but they're very expensive and very hard to come by. So if you have extra data center ready GPUs lying around, please send them our way. But that's just kind of a basic overview of the kind of problems that Link Frameworks is hoping to solve and sort of like our process of solving them, which usually ends up creating much more problems for them to us solve. So I will, as a kind of like fun advertisement for Rubin, this is the third interstellar comet ever observed, and this is actual Rubin data of 3I Atlas. It was discovered by the Atlas telescope last year on July 1st, and a paper that was recently released by our, I don't know if he's still here, but Colin, he was the first author on that, as well as the entire solar system science collaboration. Figured out that if our solar system processing pipelines had been enabled at the time, which they weren't because we're still doing the commissioning process of testing out the telescope, we would have discovered it 10 days before the other telescope. And that's very exciting, and this is sort of a taste of what Rubin is going to discover in its 10 years of initial operation.
So Rubin is in Chile, which is the equator.
Yeah.
And Rubin can take pictures of southern stars.
Yeah.
Is there an analogous telescope or ideas for identification of that north of the equator?
Yes, there is. So not at like the scale that Rubin, in like the depth, but there is, I mentioned the Argus array, which is actually going to be built in North Carolina. It is through the University of North Carolina, and it is a project that is trying to survey an actually even larger field of view than Rubin of the northern sky, but it'll be at a lesser depth, and it's sort of an experimental project to get us a wide swath of data with off-the-shelf telescopes. But generally, the focus is right now on the southern sky because that's sort of Rubin. It's easier to build a telescope in the southern hemisphere for a lot of reasons. Okay, actually, okay.
I have two questions. Hopefully, both address. The first one is why does the hemisphere add to environmental focus and Chile? And then the second one is how has the democratization of the data that we're working, how does that change astronomy and fields in general? Because we're getting significant discoveries like scientists and stuff like that.
Okay, both great questions, and both I do have the answer to. The first one, which is why in Chile, it's just way easier to build telescopes in the Atacama Desert. In the northern hemisphere, because the northern hemisphere is where the majority of people on Earth live, people live near very high peaks where you would normally want to put a telescope, like in Mauna Kea or in the Canary Islands, one of the two biggest sites for astronomy in the northern hemisphere, but people live close to those, and they don't like you building a bunch of telescopes in the mountains. The Atacama Desert is this very massive high desert where there are lots of peaks where you can build very nice telescopes and spend lots of money to build a very deep sea telescope. So it's just, and there are also very few people live in that region in Chile, so it's just easier to build a telescope. And as to the question about democratization of science and sort of like citizen science people, yes, there are 100% plans for not just like less funded institutions, but for like citizen scientists and projects to allow non-astronomers to actually get in and help like do astronomy research through like sifting through lots of data. There's a project called like Zooniverse, which is kind of developed around that, and I think also Colin over there has developed some projects for doing citizen science stuff with even like non-astronomy researchers. So I'm not an expert on this question, but I will say most of the like the most hazardous asteroids have already been recovered. And really, like when it comes to potentially hazardous asteroids, the stuff is not the like stuff that like wipes all of us out. It's the stuff that wipes like just a little bit of us out. So just like like a city or like a region or a country, but not the whole Earth. Because the bigger ones are like brighter, so they're easier to find. Whereas the dimmer ones, which will do major damage, we haven't found all those yet. But there is a congressional mandate to discover as many of those as possible, and that is a huge part of Rubin funding. Jake, do you know the actual percentage of like what the predictions are for potentially hazardous asteroids for Rubin off the top of your head? Yeah.
30% 140-meter ones.
Okay.
Rubin should get us up to 70, 80%.
Okay. So 90% of the ones that blow up the Earth, we currently know 30% of the ones that blow up as part of the Earth. But we're going to get to 70%, so be excited for that. The best programming language is the one that works for your problem. I don't know. I don't have strong opinions. I like, Python's fine. We write in Python. Really, I would like everyone to use Julia because that one's like fast and also easy to use like Python. But the worst part of academic programming is like, I don't know, like reading strong code. Not that it's like not that it's terrible, but it's just not how I would want it, and it's kind of a me problem. Like I'm very particular about how it's written. So, but that's my job, so that's I deal with it. It's fine and it's fun.
So you mentioned utilization of GPUs
Yeah.
a few times. Do you ever see a future where ASICs will be utilized for your computes? Or do you think you'll always need the general compute that is available in something like a NVIDIA or AMD?
Did you say asyncs?
ASIC.
ASIC.
An ASIC is a FPGA or some other hyper specialized piece of hardware that's
Okay.
really good at solving one problem but pretty bad at everything else.
Yeah.
Classic example is the computers.
Yeah. Okay. I think personally, it's a good question. I don't know much about ASICs, but I do think GPUs are always going to be useful, just because they kind of hit that like middle balance between like general use and hyper specific, like hyper fast computation. So that would be my guess, but I don't know. I don't really know. Yeah.
Thank you.
Thanks. Yeah.
One more.
Okay. I have one more question. I think you had your hand up, so I'll give it to you.
For both the hardware and the software side, how much of development of new technology is iterative versus complete?
Oh. Yeah, we, at least within like linked frameworks, we're very like iterative. Our sort of like main kind of like design philosophy is that we sort of develop these like core tools, and then we actually go to astronomers and have them like use it and then complain to us about how it sucks and then we make it better. I think maybe for like actual sort of like data product generation and stuff, it's maybe a little more complete since it's been developed over 20 years of a development cycle. So you just need to be able to be more strict with it. But for our purposes, we can do whatever we want. So we were very iterative with it. Yeah. Okay, I think that's all the time I have. So thank you.
All right. Thank you to Pip and Maxine. Let's thank our wonderful speakers again. Thank you all so much for coming to Astronomy on Tap number 107. As a reminder, next Astronomy on Tap number 108 is at Stoop Ballard. Please do not come to Capitol Hill. It will be in Ballard. I hope to see you all there. If you won trivia, make sure to come up and get a prize at the end. Thank you all for coming. Have a nice night.